Hello, my rubber hearts. I am back in my happy place, but this time only as a guest of gradient compounds. On this episode, I'm taking you into the lab to see how the Decrosslinked rubber actually behaves during reprocessing. I worked with two compounds, one based on butyl rubber and one based on AEM. The butyl compound was originally sulfur-cured, while the AEM compound had been peroxide-cured. My goal here was simple: to reintroduce a standard curing package to each decrosslinked compound, process it like any regular rubber mix, and test its cure behavior and mechanical performance, without using any extraordinary processing steps. Everything you will see here was done using conventional equipment and lab procedures, exactly as you would use with a normal compound in an industrial setting. I started by adding the appropriate curing package to each compound directly on the roll mill. The butyl compound had good plasticity right from the start. It handled smoothly and sheeted off without issue, very close to what you would expect from a fresh compound. The AEM compound, on the other hand, looked unpromising at first. It was powdery, crumbly, and hard to gather into a sheet. But after working it on the mill, the structure improved visibly. It began to form a consistent sheet with a smooth surface, and by the end, it showed excellent processability. This ties back to something discussed in the interview with Gradient Compound CEO. After decrosslinking, reformulating the compound by reintroducing curatives, plasticizers, or other volatiles lost in the original vulcanization can significantly improve the handling and final properties of the material. So let's keep in mind that what you are seeing here is the default processability after adding only the cure package. And even in that state, the material was workable. I can only assume that with proper reformulation, including the addition of process aids, the processability would improve even further. Let's start with the butyl compound. The cure curve in blue shows the decrossling material without any added cure package. You can see the torque increases slightly, but then levels off early. No meaningful vulcanization is taking place. Once I added the sulfur-based curing system, the orange curve shows a strong increase in torque. The cure develops quickly and plateaus smoothly, indicating a well-formed cross-link network. This is exactly what you want to see in a revulcanized rubber. Evidence that the network can be rebuilt using standard curing chemistry. Now here we see the AEM compound. Again, the blue line shows the decrossling material without added curative. Interestingly, there's a moderate increase in torque even in this state. That is because peroxide-cured compounds can retain some unreacted peroxide or coagents after the first vulcanization cycle. So we are seeing residual curing behavior here, which is not unusual for a peroxide system. But what is more interesting is the orange curve. After I added a fresh curing package, the torque rises much more sharply and reaches significantly higher levels, confirming that the decrosslink AEM material is fully reactive and capable of forming a new crosslink network. There's also something worth pointing out at the early stage of the curve. You can see a slight drop in viscosity after adding the cure package. This supports the idea mentioned earlier. Reformulating a decrosslink compound can restore processability by reintroducing key volatile components lost during the original cure. After milling, I pressed plates from each compound using time and temperature settings based on the MDR data. Once cured, I cut dumbbells for tensile testing. The actual tensile test was performed on plates that had been vulcanized 24 hours before to respect the minimum time required by the ISO 37 standard between curing and testing. After testing, I evaluated the mechanical performance of both reprocessed compounds compared to their original virgin formulation. The data is normalized as a percentage of the original values. For the AEM compound, the MDR data shows a higher minimum torque, indicating increased viscosity after decrosslinking. This aligns with what you'd expect from some loss of plasticizing components during the original vulcanization, which weren't fully replaced. Looking at the tensile properties, the AEM compound recovered around 90% of the original tensile strength. While not exceeding the virgin compound, this is still a strong result for a fully decrosslinked and reprocessed material. Elongation at break wasn't fully recovered, but it still performed reasonably well. The butyl compound showed solid performance, reaching about 103% of the original tensile strength. The elongation at break was lower, around 69%, but still within a workable range. This reflects something David Brown mentioned in the interview episode. In some cases, elongation can be almost fully recovered, but not always. The degree of recovery depends on the polymer system, the curing chemistry, and the reformulation. And again, this was tested using 100% decrosslink material. In a real production setting, where a maximum of 30% reclaim is typically used, the impact on mechanical properties and processability would be significantly smaller. These results reinforce what we saw in the MDR. With proper reformulation, the crosslink rubber can be reprocessed and revulcanized using standard methods, and it can deliver meaningful mechanical performance. These lab results confirm what Gradient Compounds had been saying. The crosslink rubber, when reformulated correctly, can be brought back into production workflows and behave like a functional compound. It processes well, it cures properly, and it delivers measurable mechanical performance. If you haven't seen the interview episode yet, I highly recommend you watch it for more context on the technology behind this process. And if you have questions, feel free to drop them in the comments. Thanks for watching, and until next time, stay elastic and stay curious.